This is Lesson 1, How a Turbine Works. In this and following lessons, you will learn about the basic principles which make the turbine engine a highly reliable power producer. Understanding how the engine works in the most basic terms will allow you to build your knowledge of these complex processes more quickly and thoroughly. This lesson addresses these processes at a fundamental level and provides the foundation for the remainder of the course. When you finish this lesson, demonstrate your understanding by taking the progress check on the following performance objectives. 1. List the 4 processes of engine operation. 2. Identify the location of energy conversion into useful power. 3. Name the 2 ways expanded gas is used by the turbine rotor. Your instructor is Don Lovejoy.
The industrial turbine engine is an internal combustion engine which produces horsepower by using the energy of highly compressed air mixed with fuel and ignited under special conditions. It is in the ignition and combustion process that heat energy is produced, which is converted into power useful for work. Continuous operation of the engine requires that 4 processes occur. Compression, atmospheric air is compressed. Combustion, fuel is added to the compressed air and ignited. Expansion, air and combustion gases expand through nozzles. Exhaust, air and combustion gases are discharged into the atmosphere. To begin the process of energy production, air is first drawn into the compressor, where rows of blades compress the air into an increasingly smaller space. Energy to turn the compressor is first supplied from the external start system until the turbine has enough power to turn the compressor over by itself. After the air leaves the compressor, it enters the diffuser area. In the diffuser, an additional pressure rise occurs. The pressure at the exit of the diffuser is about 118 pounds per square inch at operational speed and full load, right about here. After the air leaves the diffuser, it enters the combustion chamber, where either liquid or gas fuel is added to the air. This highly pressurized air and fuel mixture is then ignited by a fuel-fed torch. The combustion process releases the energy of the fuel in a temperature rise in the combustor, and after ignition has taken place, the hot gas expands very rapidly so that its velocity and its volume increases. The average temperature in the combustion chamber is about 1600 degrees Fahrenheit. These hot gases expand through the turbine section, deflect the turbine rotor blades, and turn the turbine rotor. The turbine rotor then produces the power to turn the compressor and produces the power to turn the electrical generator. As the expanding gases flow through the turbine section, their temperature and pressure drops, and they ultimately exit the turbine into the atmosphere through the exhaust diffuser.
Now that you've seen the basics of how a turbine engine works, review what you've learned. The 4 processes which permit the engine to operate are compression, combustion, expansion, exhaust. Energy is converted to useful power at the turbine rotor. The turbine rotor provides power to drive the compressor for sustained operation, the generator for electrical production. You have seen how compressed air and fuel are combusted and how this rapidly expanding hot gas is used to turn the turbine rotor. Smooth operation is achieved by transferring some of this power into further compression of air. The turbine engine is a heat engine. converting heat energy into power. Each of the four processes contribute to the uniform performance of the engine and will be examined in more detail in the remaining lessons of this module. This is Lesson 2, Understanding Air. This lesson is about air. Air is the most critical requirement of the turbine engine. The way air behaves explains how the engine is able to produce power. In this lesson, you will learn some interesting and important facts about air. These facts explain why the turbine engine can use air to great advantage through energy conversion. At the end of this lesson, you may demonstrate your understanding by taking the progress check on the following performance objectives. 1. Explain the terms temperature and pressure. 2. Describe the relationship between pressure and temperature. 3. Describe the effect of compression on pressure. 4. Describe the relationship between pressure and velocity. Now here is your instructor, Don Lovejoy.
The turbine engine uses heat and pressurized air to perform work. There are several properties of air which should be kept in mind in order to understand how air and heat are put to work. These properties explain how energy is converted from one form to another. The turbine engine is designed to take maximum advantage of energy conversion. We know that air consists of minute particles invisible to the eye called molecules. Molecules are in constant motion, colliding with other molecules and with the walls of any container which hold them. Temperature is simply a measure of the speed of molecular motion. When air molecules are moving slowly, we measure a low temperature. But when molecules are in rapid motion, the temperature reads high. When molecules are enclosed in a container, some of the molecules will strike the walls at all times. The faster they travel, the more force they strike the wall with. This force is measured as pressure. Since temperature is a measure of molecular motion, if we add heat to a container of air, the molecules move faster. Heat energy is transferred to energy of motion. But when air molecules move faster, they exert greater pressure. So temperature and pressure are closely related. In fact, for each increase in temperature, there is a corresponding increase in pressure. Another property of air which is important to turbine operation is compressibility. If we attach a pump to our container, we can add more air molecules to those already there. Should we continue to pump air into the container, we would see the pressure rise. It's easy to see why. With more molecules, the number striking the wall at any single moment increases. Since each molecule exerts force on the wall when it collides, it makes sense that pressure would increase when more molecules are pumped into our container. So energy has been converted into pressure through compression. Now there's one final but extremely important property of air. In order to understand it, we'll have to take the air out of the container and put it in a pipe. Let's add a reliable, steady air supply which will deliver a constant flow rate to the pipe. Remember that air flows through the turbine engine in a similar fashion. The air has temperature, pressure, and a forward velocity provided by our steady air supply. Now observe the result of constricting the pipe to half its diameter. Since the constriction must move the same amount of air as the larger pipe section, air must move through the reduced pipe faster. Failure to increase velocity in the narrow pipe results in blockage and reduced flow. But we see the velocity does increase. Energy is required to increase air velocity, and the energy required here comes from the existing air pressure. As energy is converted from pressure to velocity, we see the air pressure drop. When air flows into a constricted flow path, we observe a velocity increase and a pressure drop. If we allow the air to flow back into a pipe of the original size, the flow is now handled at a lower velocity. Since the velocity of air decreases, excess energy is converted into pressure increase. When air flows into a larger pathway, velocity decreases and pressure rises. In the turbine engine, the unique relationship between pressure and velocity explains many operating principles. In the compressor, the air is slowed and compressed. In the combustor, the air is heated and expanded. In the turbine, the air is speeded up to be used to turn the turbine wheels, and then is exhausted into the atmosphere.
Let's take this opportunity to review what you've learned. Temperature is a measure of the motion of air molecules. Pressure is a measure of the force of air on a surface. Temperature and pressure are directly related. An increase in temperature results in an increase in pressure. Compressing air causes pressure to increase. Pressure and velocity are inversely related. As pressure goes up, velocity goes down, and when pressure goes down, velocity rises. Air is used to convert energy from one form to another. You know that heat can be added to air to increase the pressure. Likewise, by adding energy through compression, the pressure will increase. By altering the air flow path, energy of velocity can be converted to pressure energy. In each case, air is used to convert and transfer energy. What you now know about air can be applied directly to the turbine engine. In the next lesson, you will learn how the engine is designed to... This is Lesson 3, Principles of Compression. In this lesson, you will learn about the compressor and how compression is achieved. You will see how the compressor is designed and will study the effects of compression on air. Your understanding of these concepts will help you in dealing with routine troubleshooting and maintenance related to the air system and engine start sequence. At the end of this lesson, you may demonstrate your understanding by taking the progress check on the following performance objectives. 1. Describe the basic features of the compressor. 2. Explain what happens to air velocity, pressure, volume, and temperature in the compressor. 3. Explain the term diffusion. 4. Describe ways the compressor maintains air velocity. 5. Explain the term PCD and identify where it is measured. Here is your instructor, Don Lovejoy.
The principles of compression are best understood by first looking at the construction of the compressor. The flow path is formed by an annular passage around the rotor assembly. As the air flows along the length of the compressor, the air path decreases in size. Since the path for the air is parallel to the rotor axis, the compressor is an axial flow type. The work of compression is done by several rows of blades, similar to the blades of an electric fan.